There we go. Okay, so we're now ready to go. And as I said earlier, you can ask questions as we go. There is a section in ISO and EN which are very similar standards. They're virtual copies of each other. Section 7.8.2, which talks about hold times to be determined by the door fan. There are sections in there that talk about peak pressure evaluation, and it's pretty well known in Europe, the Middle East, etc., that a peak pressure evaluation has to be done. So today we're going to be talking about the balance between a hold time evaluation and a peak pressure evaluation. The main standard that we're looking at is the 2006 edition. 2006 edition uses what's called the wide interface model. And when you're running the software, I'll just bring our software up, drag it over to the screen here. There is what's called an HE calculation that would be easy to miss. And it's right down in the equivalent sharp interface height, HE. So how the ISO standard or the ISO formulas calculate this wide interface is by putting in what they call an artificial equivalent height, and thereby establishes the appropriate place in the middle of this so-called wide interface, which is currently in effect, but we have proven through 5 years of research that it actually doesn't go that way, and have created a new model that's been accepted in the latest version of the ISO standard, which is called the thick interface, and it removes some of the unnecessary conservatism of the wide interface model that we will touch on later. The standard also requires that protection be held to 90% of the enclosure height. As we will show later, that forces a much tighter enclosure and makes it extremely difficult to pass the hold time requirements, and forces the use of pressure relief vents in almost every case. We will investigate that by using one of the new features in our software, which is called the design, what's it called here? Let's just bring it up. It's called Enclosure Leakage Design, and it's this window here, the very first window, and we also call it the venting calculator. I'm not quite sure why. And the venting calculator is a window that looks like this, that allows you to do an evaluation of an enclosure in the design phase and look at all the various parameters. There's also a mistake in there in E3.4.2, which should read F equals 0.15, which is actually quite important because it means that that whole section doesn't make sense if you read it the way it's written. All you really have to concern yourself with is not so much perfect understanding of the standard. Our software does the test according to the standard, so you simply have to follow the steps in our software and go through it, and it will give you a compliant test. This is the section that talks about pressure venting requirements, 7.4.1, that the enclosure should have sufficient strength to contain the agent discharge. So that kind of implies that you need to know what the pressure is going to be in the enclosure, and by measuring the enclosure leakage or the enclosure and vent leakage, we can determine whether or not it has sufficient strength to contain the agent discharge. That also requires that there is a specification for the structural strength of the enclosure. which typically would be in the range of 250, 500 to 1,000 pascals. So a lot of what we know about this was evolved over a period of about 5 years, 2 intensive years. We had a team of Fike, 3M, DuPont, Kidafenol, Chematron, Ansel, Wormald, Retrotec that tested all of the inert agents and all of the halocarbon agents that are most commonly used in a test chamber and varied the leakage of the chamber and plotted the peak pressure that was generated. And we discovered that the peak pressure formulas that were in use at the time were not consistent with our experimental results. These are the different agents that we discharged. These are the different years and the different tests that we did, 2004, 2005, 2006, 2007. You might say, oh my God, you know, that was 2007, that was many years ago. This doesn't sound like recent news. Things happen quite slowly in standards evolution, and it usually requires about 2 or 3 years for experimental data to filter through the standards committee and the standards writing process. And it's something that I've had manned both for the ISO and the NFPA standard, and eventually gotten the descending interface part into the ISO standard, but not the peak pressure part, which is not actually included in the standard, and people tend to use a wide range of peak pressure formulas, which is unfortunate because they do, the different formulas do give very different results, as we will see. This is another table of different experiments. We go back to 1997 and different discoveries that were made and the peak pressure range that were that the tests were done over. What you notice that some of the earliest data that was taken is that the peak pressure range is a relatively minor. So in 1997, they did 18 tests. Great Lakes did 18 tests between 260 and 370 pascals with a leak to volume ratio of 2.3 to 3.3. So over a very narrow range, the range that was used earlier than that was over a range which is not consistent with the leakage range of the enclosures that we're encountering. So getting those to coincide was the reason why the peak pressure formulas that are out there aren't as relevant as they could be. So the measure that we utilized for evaluating enclosures was the leak to volume ratio. So we were able to plot the leak to volume ratio versus the peak pressure. You can also use the peak discharge rate. Leak to volume ratio and peak discharge rate are somewhat synonymous. If you have an enclosure of a certain volume, it's going to take a certain amount of time to fill it up, essentially, and it kind of boils down to the same thing. But leak to volume ratio is actually a lot easier to understand than looking at peak flow rates. The other problem with peak flow rates is that there is still the guess as to what happens when these various peak flow rates go into an enclosure, and it's always been assumed that the enclosure responds in a square root function. It's not a square root function at all. It's about a 0.9 function. So that was one of the first discoveries that we made. So this is what a peak pressure looks like for an inert. A positive pressure spike, followed by a decline. Positive pressure spike happens in about the first 4 or 5 seconds, and then it declines to next to nothing. This means that the agent is flowing into the room extremely rapidly at first and then drops off very, very quickly. this was all the experimental data that we took for inert. You'll notice that if you take any two data points, you can establish a very, very different curve. But we took these this data over a very, very wide range of leak to volume ratios. Typically, enclosures would fall in this area here from leak to volume ratios of 20 down to 10, or maybe as low as 5. So we have it pretty well covered, so we actually know what the shape of the curve is. So that's the shape of the curve that we established, and the dashed lines are the shapes of the curves that would be achieved using a square root relationship. And you can see that they don't go in the same direction, which is the reason why we will have such big differences between the two. And at this spot here, at leak to volume ratio of 10, we can have differences of 100, 200, 300%. So it can be fairly significant. So this is another way of looking at peak pressure. The black line is we call it the FSSA data. This is the experimental data, the experimental line, which is, as I said before, is about a minus 0.9 function. The VDS curves, or the FIA curves, or all the manufacturers' curves, are square root functions. And if we assume that the peak flow rate is around 4.5 times the average flow rate, then we get a curve that looks something like this for VDS or FIA. And you'll notice that the 2 points cross at around 250 pascals actually give the same results. So what we've done in the latest version of our software is we have defaulted the VDS FIA curves, or the mass flow rate, to be 4.5 times the average flow rate, so that we get at least 1 point that's in the right place. Now the curve down at the bottom is the average flow rate. So if we were to use the average flow rate through the nozzle, then let's say 250 pascals, here we're calling out about 100 units of leakage, and here we're calling out 350 units of leakage, meaning that we need 100 units of leakage in order to keep the peak pressure below 250 pascals. Now the other thing that you're quite likely to come across dealing with inerts is what I call pressure regulating valves, and all of the main manufacturers have them now. We did have the opportunity to test one during our experiments, and found that they produce roughly about 1/2 the peak pressure that would be achieved with a normal inert gas discharge, which really makes a huge difference in terms of how much venting is required and how tight the enclosures have to be, and so on. So comparing the curve on the left, which was a typical wide open discharge or normal peak pressure discharge, to the pressure regulating valve, you notice that this flow rate kind of is more or less constant throughout the discharge period of around about 60 seconds. There's a little bit of variation from one valve to the other, but all the data that we've seen so far is, regardless of the manufacturer, all of these pressure regulating valves seem to have pretty similar results. And the equations that we currently have in our software, which we can bring up here, are listed under, let's just take a look at the different agents here. They're listed under ProInert IG55 PI for ProInert. We would like to be able to use the Tyco, Siemens, Kidde-Fenwal names in there, but they haven't given us the okay to do that yet. They're still kind of like looking at the data and stuff. What I have noticed in the peak pressure formulas that they used for their pressure regulating valves is that in the case of the Kita, for example, we get the same results they get at 1900 pascals, and we're different everywhere else. So I think that might possibly be the case of them not having tested it over a wide range of enclosure leakage. When I consulted with the research group here in the U.S., they said that they don't use the Kita curves, they use the FSSA curves for their pressure regulating valve, and we're still negotiating with them to put their name on here. However, what we have discovered is that the pro-inert values are the right ones. So what will happen when you choose those in your reports is it will say pro-inert, but you can simply go in there and change that in the Word version and change it to whatever name you want to put on there. But that is how you find the right curves for the pressure regulating valves. Now, as far as halocarbons are concerned, we found a similar problem where, again, the manufacturers were using square root relationships, and this CEA formula here with a black dashed line is a good example of that, where it's like a clock that stopped. It's right at the point where the curves cross. The shape of the curves that we're getting for the halocarbons are very different. They are nowhere near square root relationships. But we do know what the shape of those curves are now, and they're all included in the FSSA curves, which we're recommending that everybody uses. They have been taken on by FIA, for example, in the UK, and FIA uses the FSSA curves for peak pressure evaluation of halocarbons, not of inerts, but of halocarbons. This is a little comparison table of FSSA versus existing formulas, so we can see what the difference is. We won't go into that in a lot of detail. An important thing to know is that the leakage of the enclosure directly affects the peak pressure. If we have the enclosure leakage, we double the peak pressure. It's actually pretty close now to a linear relationship, linear inverse relationship, I guess. And this shows that as the enclosure gets tighter, then the negative and positive pressure pulse become greater. And we discovered, much to our amazement, that often the negative pressure pulse is the larger of the two. And it's also dependent upon humidity. So the drier the enclosure is, or the drier the air is that the agent is discharged into, the more the negative pressure pulse. And we can use our software to play around with humidities and see how that affects it. This curve, the red curve here, shows when the humidity goes from 0 or close to 0 down to 70%, that the humidity correction factor decreases, meaning that if we had a peak pressure here of, let's say, 1600 pascals at 10% humidity, then our peak pressure would only be around 400 pascals at 70% relative humidity. The effect on positive peak pressure is relatively minor by comparison. There, as the humidity goes up, then the peak pressure goes up a little bit, so it goes in the opposite direction. But it could just be by virtue of the fact when the enclosure is driven very far negative, it requires a lot more agent to drive it positive. So the negative spike always occurs first and the positive spike occurs afterwards. So the size of the negative spike actually affects the size of the positive pressure spike, which is actually caused by primarily the nitrogen blowdown in the tank, which is acting like a small inert agent discharge and providing a positive pressure spike. The reason why we get a negative pressure spike is that we have a huge amount of cooling that goes on in the room, which we will see in this slide here. And we see that the temperature has dropped. This is in Fahrenheit, unfortunately. It's dropped from 70 degrees down to 45 degrees in around about, what is that, 6 or 7 seconds. So a massive thermal shock in the room. Both HFC 227EA, FM200, or Novak perform very similarly. As you can see, the slope of the curve is relatively the same. They don't produce exactly the same negative pressure spikes because the heat content of the agent is different, but they are similar. So we're talking about 28 degrees F here over a very, very short period of time compared to, say, IG55N inert, which has a very, very slow taper, only 13 degrees Fahrenheit pressure drop, but more importantly, over a very long, protracted period of time, so that there is not much or no negative pressure spike, but the little bit of cooling that happens with the inert does reduce the amount of the positive pressure spike that is felt. So the mistake that we've made in the past when evaluating peak pressure is we're looking at it as a pure flow rate formula. In fact, it's really a thermodynamics issue where we've got agent being blown into the enclosure, we've got cooling going on, we've got all kinds of effects happening, so it's not simply just a flow rate, Bernoulli's theorem, etc., with air blowing through a hole and so forth. So we're just reiterating the same point. This is the characteristic curve of Novak, a very deep, short negative pressure spike followed by a positive, which is usually about half the size of the negative spike. What that means, of course, is that most of the vents in Europe that have been installed for halocarbons have actually been installed backwards. So it's important to do this evaluation and to be installing vents that will relieve the pressure in the direction that the pressure is going to occur in. And there are dual acting vents that will do that, that will open in both directions. So this is HFC 125, produces much less of a pressure spike in magnitude, but still in a very, very tight enclosure will still produce a significant amount of pressure, and it seems to have a pretty balanced positive and negative pressure spike. This is at a relative humidity of 40%. When it goes down closer to 10 or 15%, the negative spike starts to get larger, the positive spike gets smaller. So from a design standpoint, the enclosure strength needs to be specified. That will give you an idea as to what the leak to volume ratios could be, and the inputs would be the agent type, whether we're using a pressure regulating valve, the rate of discharge, and the leak to volume ratio. And that will tell us whether or not we need to have pressure relief vents. So we can run through a few of those sample calculations right now, actually. So what we're going to do is we're going to bring up our venting calculator again. And in this case, we have an example of argon. We can use argonite. The differences are very, very small. And put in a typical, I think 40.3 is typical concentration. Discharge time 60 seconds, temperature and discharge of 20 degrees. So we're using a 1,000 cubic meter volume with a maximum flooded height of 4 meters, and the leak fraction defaults to 0.5. That's the ratio of the upper to the lower leaks, and 500 pascals is a pretty typical enclosure pressure limit with a minimum protected height of 2.8 meters, which is about 70% of the enclosure height, And if you hover over these values, you can get some more information on them. And in other parts of our software, we have, I think, little light bulbs or question marks, and you can click on those and get more information as well. So once we've got those values in there, we can simply press calculate, and we get two values there that popped up. I don't think I can make this any bigger. Yeah, okay. Hopefully you can see that. So here we see that for the given hold time, the enclosure leakage cannot be more than 10,922 square centimeters, and the pressure relief vent has got to be 13,000. So if we were to tighten the enclosure down so we got exactly 10 minutes of hold time, then we still don't have enough leakage, assuming we can use the enclosure leakage in order to relieve that pressure. So if you wanted to find out just how much pressure that we'd get, we can elevate this up to, let's say, 700 pascals and do the calculation again. And you'll notice that at this point, if 700 pascals is our enclosure pressure limit, then the pressure relief vent area that we need is around 9,000. We can go down to 10,000. There's actually a little bit of a gap there. So we could actually have an enclosure of these dimensions. We could be discharging argonite. If we had no pressure relief venting at all, we would know that the enclosure pressure limit would be around 700 pascals. Essentially, what is happening here is the tightening that has to occur in the enclosure is defining how much peak pressure we're going to get. Okay? So let's say, for example, we say, aha, well, we want to protect up to 90% of enclosure height. So that's 3.6 meters. We recalculate, and now it says that we've got to tighten the enclosure down to 3.4 square centimeters. I'm sorry, what is that? 0.3 square meters. I think I did that right. 32 square centimeters. So it now requires that the enclosure be much, much tighter in order to hold our concentration at 3.6 meters in a 4-meter enclosure. So there are some ways out. One way is to say, well, let's look at the distribution of leaks between upper and lower, and let's change this to 0.15, which incidentally is the limit that you're allowed to use under ISO, and that allows us to have quite a bit more leakage, but still not enough because our minimum protected height is so high. So the other way of getting around that is to discharge more agent and go for continuous mixing. And most of the enclosures in the UK, at least, and many of them in Europe, actually have the AC units are continuing to run during the hold time, so we have continuous mixing. So let's take a look at continuous mixing and see what that looks like. So we've gone from descending interface here to continuous mixing, and here our minimum concentration will be 85% of design. So if the design is, let's just bring up a spreadsheet here so we can do some of those little calculations. So equals 0.85 times 40.3. It's 34.2. Okay, so let's do a calculation based on that. We'll take our peak pressure limit back to 500. We have to hit calculate each time, by the way. So here we still don't have a viable situation, even using continuous mixing and lower leak fraction to the absolute limit. But let's take a look at what happens when we increase our initial concentration. The minimum concentration that we're allowed at the end of the hold time stays constant at 85% of design. Just because we go from 40%, 40.3% to 50% in our initial concentration does not mean we've changed design. So when we do that, we go to 50%, you'll notice that right away that we can tolerate a much, much greater amount of enclosure leakage. That's because with continuous mixing, the concentration starts at 50%, goes to 49, 48, 47, 46, and so on throughout the enclosure. So the hold time is actually based on the gap between the minimum concentration that we have here and the agent concentration we have over here. If we make this gap very, very small, for example, you'll see that the enclosure is going to be very, very tight so that we don't lose any of that precious concentration. So let's go back to, let's see, around 41%, and they're about the same. So this is a great tool that can be used in the design phase in order to look at different parameters and to adjust the enclosure pressure limit, where in some cases people say, oh, I want the enclosure pressure limit to be 100. Okay, that's fine, but that means that we're going to have an absolutely massive peak pressure, because it's going to require that the enclosure have a lot of leakage in order to keep the peak pressure down to this limit. So no matter how many tricks we pull out of our bag, we can never get the enclosure leakage to a high enough value here that we can get around using pressure relief vents. So we will always have to use pressure relief vents if we say that our enclosure pressure limit is 100 pascals. 100 pascals is a very, very low pressure. It's about equivalent to, if you slam the door really hard, you'd probably get 100 pascals. I just slammed the door on my car the other day and I got 75 pascals pressure spike. So kind of puts that in perspective. Even the flimsiest walls will handle 100 pascals. We test with the door fan at 50 pascals. Our new door fans will easily go up to 250 pascals. So in some cases where they were concerned that the rooms wouldn't take more than 100 pascals, I would just turn my door fan up to 250 pascals and say, well, it's taking it now. There is no difference between running a constant static pressure from your door fan and the peak pressure spike. And the people that I've talked to, the PhDs and so on, say that the pressure spike won't do any more damage than a constant pressure of 250 pascals. So something to bear in mind. So this is a great little tool that allows you to do all those comparisons before the enclosure is designed, to make adjustments to your thinking, so that when the tester gets on with the job site, he's not left with an enclosure that can't possibly be passed. In this particular case, if we're looking at continuous mixing, we can be adjusting these initial concentrations and find out what they are. So let's just go back to a reasonable peak pressure value of 500 pascals, put a reasonable lower leak fraction of 0.25, which is something that you have to measure, by the way, and we'll get on to how we measure that later. Go back to calculating. So now we're kind of in the range here where probably for a hold time of about 11 minutes. Let's see, what does 11 minutes say? We're kind of in the range, so if we tighten the enclosure down to around about the 11-minute mark, we would not need a pressure relief vent at all if we were going to rely on enclosure leakage. Now, we have a really different philosophy between one group, primarily in North America, that says, well, we can rely on enclosure leaks, to the group in Europe who primarily say that they cannot rely on enclosure leaks. Somebody might magically come along in the middle of the night and seal them all up, although I've never seen that actually happen. They want to rely on a pressure relief vent, so they ignore the enclosure leaks. Our software will allow you to do it either way, so that you can rely on enclosure leaks only. PRV leaks are pressure relief vent area, or free vent area of the pressure relief vent itself, or both, whichever way you want to do it. Which sometimes causes more confusion, but I'm sorry, that's the way it is. So let's go back to, we've touched on the designer tab. We have all kinds of warnings in there about using various equations and the defaults that we've used and so on. One of the chief warnings that we have there for using VDS equations do not admit that there is a negative pressure pulse. They only calculate a positive pressure pulse, and there definitely is a negative pressure pulse. The negative pressure pulse is the larger of the two in most instances and should be calculated. We strongly recommend that you use the FSSA or FIA calculations for doing halocarbons. So this is fantastic integrity. It's been totally redone. We have a multi-point test in there for ISO and so on. We're now calculating the hold time and vent area requirements and peak pressure evaluation all in one package. Produces a wonderful report that puts all this into Word report. Could also put the data out in Excel if you want to do it that way. You can customize the templates so that you can take a task, which typically takes us about 2 or 3 hours, and we can do it in about 15 minutes now using the reporting function, which is built into the software. You can either go to File, Generate Report, or when you're on that screen and you're doing the hold time analysis, there's a little button down here that says Generate Report. And we do the same thing under venting. I think there's another button down here that says Generate Report. So a number of places to locate the report button. It was always there. And it's a feature that is included with our licensed software version. So the current versions of our Fantastic Integrity software will give you an example test, but won't give you your particular test. So we're restricting the Word-generated reports to licensed users. So there we have a picture of a dual acting pressure relief vent. Opens in both directions, and we prefer that they open about -80, +80 in that range. And we do recommend that every PRV used be tested. Sometimes they're out by a wide margin, and there have been some enclosures damaged severely due to the fact that they used the wrong units or got the wrong values in there somehow, or they were stuck or whatever. Should be able to turn your door fan on the enclosure and see the vent open in the positive and the negative direction quite readily. And if it doesn't do that, then there is probably something wrong with the vent or the venting path, which could be the other problem. So the vent might work fine. It might be attached to a duct that's not allowing for flow, or might be blocked in some other way. So a key part of the process now is to measure the enclosure leakage for hold time and also to measure the pressure relief venting path, which assures that you actually have the venting that you know you have. This is a new fan configuration that we evolved, which is called our contra fan. It's 2 of our fans connected together, but they're not running in the same direction. We've got one running clockwise and one running counterclockwise, and they will test PRVs well over 500 pascals. But at high flow rates at 5,000 CFM. If you need something like that, we can provide it for you. But we recommend that you take your PRVs, mount them into a box, and depressurize the box so you're not blowing air at the PRV. Turn the PRV around to test it in the other direction to make sure that they open at the prescribed pressure. You can also measure the free vent area of the PRV using your door fan using that method. There's a little hold time. This is the ISO 2000 version used the sharp interface. The 2006 version used the wide interface, and the next version we use the thick interface, which is kind of somewhere between the two of them. The wide interface that came out in the 2006 version was extremely conservative and would give hold time predictions that were roughly a half of what they should be. So often enclosures that should have passed were failing miserably using the wide interface. And it assumed that the interface starts to spread, and which it doesn't do exactly the way they assumed it did. When we measured it, we found it actually spread in a very different way. It went to a characteristic thickness and spread from there. But the cooling effects that we had both with inerts and with halocarbons drastically affected the way the interface formed and the effect of the interface, such that particularly with halocarbons, there was so much contraction in the enclosure that for the first 4 or 5 minutes there was virtually no agent loss at all. Very, very small amount of agent loss compared to what the equations assumed. So as we will see later, that had a big impact on the results. So here we have sharp interface, that was the original one, the wide interface in ISO 2006, and the thick interface, which has already been accepted by the ISO committee. We have all the final wording in there, and the next time you see an ISO standard, it will have what's called a thick interface with all of the equations and the research information that we put into that, which is going to give you longer retention times than you're getting right now. So that only took about 5 or 6 years to get that done. But it means that enclosures won't have to be tightened up as much as they are now. The requirement for holding concentration to 90% of the enclosure height has been removed, and it's been changed to the height of the highest hazard or the equipment that's being protected. So in all cases, it will mean that enclosures in the future won't have to be air sealed quite as tightly as they were before, and we won't be so reliant upon the pressure relief vents, which is going to make the enclosures safer, I think, because they don't have the potential of developing such high peak pressures, and much less expensive to produce with, as far as we're concerned, no change in the protection part of it. This is what the interface actually looks like for those of you who care. The dotted line is what our new equations do, and this is agent concentration as a function of the initial concentration, which is 1. So we're typically looking at the 0.85 or 85% of the initial or of design as the area of interest. So this is the primary area of interest. Sometimes our area of interest stretches down to a lower concentration than that. But this is our primary area of interest, and this is where our equations work extremely well for the new thick interface analysis, which you don't have to worry about at the present time, just to know that things are getting better. This is what the interfaces look like. IG100, which is nitrogen, has no interface, no cylindrical interface at all. There are equations in there that says the agent ascends, the agent descends. Actually says the agent ascends. It actually doesn't. It descends initially, it sits in the middle and does nothing for about 4 or 5 minutes, and then it starts to ascend slightly towards the end. No discernible interface could be found using 3 discharges. So we have been always recommending for the last 10 years that nitrogen, or IG100, only be used in the continuum mixing mode, and that the density difference of the agent is used as the driving force, which we still maintain, and our software still runs that way, and it still works fine and gives you good results. So here is IG55 hold time versus height. This is the data that we got. This is the NFPA, which is a little bit optimistic. And this is the existing ISO formulas, which are a little conservative. So if we were to look at that in a different way, we'll notice that NFPA here is a little bit conservative. ISO is a little optimistic, and the new proposed values are right smack dab in the middle. Novec, you can see with Novec, the data and the NFPA line are actually pretty close to each other. They cross at this point. And they're a lot closer, and we can see that here the ISO formulas are roughly around 35% optimistic. So they're going to be yielding peak pressure times, or I'm sorry, hold times, which are extremely conservative. And this is where the new proposed line will come in. So we basically hit it right on the money. And the old NFPA curves, which is ISO 2000, were a little bit optimistic by about 15%. This is FM200, and here FM200, the NFPA curves and the data are almost coincident. They're almost right on top of each other, again because of the cooling, and the ISO is again very conservative. Our proposed values are a little bit conservative, but not anywhere near as much as the existing ISO formulas are. This is probably the range of interest here. So here the ISO formulas we would be predicting around about, what's that, 500 seconds. The actual will be around about 800 seconds. So it's about 35–40% conservative. In the worst possible case, most of the time the retention times or hold time is going to be much, much longer than that, but this is the worst case. It's always going to be 40% conservative, and as I said before, requiring that the enclosures be tightened up much more than they have to be. This is again IG100. So we've just about run to the end of our presentation. It's 9 o'clock, so I can understand that you know, some of you might want to go off and do something else, but I'm going to run through the sections here on the options to reduce the size of the PRV or possibly eliminate it altogether. And there's some important pieces of information here. One is that we need to establish the enclosure pressure limit. These are the rules of thumb that I use for 2x4 walls, 250 pascals, 500 pascals for 2x6, 750 pascals for 2x8, and 1,000 pascals for reinforced concrete. Not necessarily concrete block. Concrete block, unreinforced, may not hold much more than 2x4 or 2x6 wall. They can actually be cracked fairly easily. They need to have rebar, and they need to be pinned at the top and bottom. Some of the enclosure failures have been caused by concrete block walls. Concrete block walls will also produce higher peak pressure values than gyprock walls simply because they don't give. That's not reflected in any of the peak pressure formulas, but the increase in pressure is around about 30–40% because there's no movement in the wall whatsoever. It just stays absolutely stationary, and when it goes, it tends to fail catastrophically because the blocks crack. So be careful with unreinforced concrete block walls. So comparing agents, something that you can do with the enclosure leakage design tab is to look at different agents and you look at their peak pressure values and retention times and so on. They're not really that far off. We used to think that inerts were the ones that created all of the peak pressure, but the difference is that in order to get the retention time down to the same zone, we've got to decrease the leakage of the enclosure by a factor of almost 3, which tends to create more peak pressure. So you can see here with a 40% inert and a 7% FM200, the peak pressure values are pretty similar, 507 versus, that's on the positive side for the inert, 337 for FM200, 386 for Novec. They're kind of in the same order of magnitude, certainly. So we cannot ignore halocarbon peak pressure and do need to do an evaluation on all of them. This is an important tip would be to close isolation dampers that will be isolating the building HVAC from the enclosure at the end of the discharge instead of at the beginning of the discharge. There's very little agent loss when the dampers are closed as long as the system behind them has been deactivated. Obviously, if that system is running and it's going to be sucking air or agent out of the enclosure and allowing air to be blown in, that's not such a good thing. Even at that, the pressure venting aspect of the keeping the isolation dampers open has a fair bit of value. So something that should be considered, particularly in situations where you have no ability to install a PRV or the enclosure is already built. 4 other ways are to increase discharge time. That can also be done with the new pressure regulating valves, which effectively decrease the greatest spike in the pressure discharge to lower values of concentration will reduce it somewhat, not very much. Raising humidity for halocarbons, usually you don't have any control over that. You do need to investigate the systems that control humidity in the enclosure. So 5 options to increase hold time would be to specify continuous mixing. This is particularly important wherever in your jurisdiction, if they are requiring 90% of enclosure height, that the descending interface be held to 90% of enclosure height, that it's almost mandatory to use continuous mixing. It's almost impossible to pass these enclosures with the HVAC or the recirculating air conditioning systems off at 90%. So you're actually much better off to increase the amount of agent by about 20%, keep some recirculation happening within the enclosure, and rely on continuous mixing. A lot of people have never even heard about continuous mixing or don't know it exists. In fact, it's there probably 50% of the time at least, so something everybody needs to become familiar with. And there we're running 2 tests, one descending interface getting a 5.1 minute retention time. Here we're running one continuous mixing getting 13.9 with exactly the same amount of enclosure leakage of 200 square centimeters. Same agent, same everything. So that's typically done with the dedicated HVAC in the room where you've got air conditioning units usually blowing into the floor and the cool air coming up onto the equipment and just going around and around. Whenever you do that, we do need to, in the software, to tell the software that during the whole time that the pressure that's in that subfloor will be there and has to be added in because it will help to push the agent out of the enclosure. So I can show you where that is in the software, hopefully. I think it's under building and extinguishing details. Just take a look here. Bias pressure during hold time, PBH. So that's the one, that's the place where we need to put the pressure that will be in the subfloor or any bias pressure that will be in the room or we expect to be in the room during the hold time. Comparing agents, we did this already. Extended discharge, which is quite commonly used for CO2, not as common in other areas. This allows us to have very, very leaky enclosures which don't necessarily need pressure relief vents. And by running the software using extended discharge, which is one of the options here, continuous mixing, this one doesn't do extended discharge, sorry about that. Extended discharge, we're able to determine what the agent loss rate is, and then we simply need to continuously discharge the agent at that loss rate for as long as we want a hold time. So if we're going to lose, let's say, 20 kilograms a minute, we need to discharge at 20 kilograms a minute and to continuously mix the result. So that will give us any kind of hold time we want as long as we keep continuously discharging at our loss rate. Now, this reduced hold time, this might be appropriate for very, very small enclosures where there's not a lot of mass there. They tend to be particularly difficult to pass the whole time evaluation, and small enclosures of, let's say, 10 square meters floor area and less are very, very difficult to pass because the volume is very small. There's a lot of surface area there and so on. And there is no reason why we need to have a 10-minute hold time in those enclosures. It could be 2 minutes or 4 minutes or whatever. So that's something that does need to be considered. On the other side of it, if we're dealing with a remote enclosure and the response time is, let's say, 30 minutes, then we might need to have a 30-minute hold time. So that's something that needs to be done at the time that the system is designed. And of course, reducing the lower leaks, and it's a matter of reducing the lower leaks, but also measuring them. And here's the effect of putting in different lower leak values. In this case, the total leakage can be 30 as long as the lower leak is only 6. So we can have twice as much leakage as we had before and still get roughly the same retention time by measuring the lower leaks, which we can do by putting plastic on the ceiling. This method is allowed from ISO section 3.4.2, I believe. It's being fleshed out and reinforced in the new standard. The software does handle lower leak testing, which putting plastic on the ceiling is one way to measure a lower leak. And the second way to do that is to use one of our double fans and flex duct systems, where the flex duct neutralizes the pressure across the ceiling, allowing the lower fan to measure the lower leak, which can now be inserted directly into the software and will increase the retention time by a factor of as much as about 3. So for enclosures that have a 3-minute retention time, the first thing I ask is, can we use a BCLA test or a below ceiling leakage area test with a double fan and flex duct in order to measure the size of the lower leak, which would allow that enclosure to pass. And this is a schematic of it. The second fan is taking care of the upper leaks. The lower fan is taking care of the lower leaks. There's another picture of it. ISO allows a maximum of 85% of the upper leaks. They don't let you go beyond that, or the lower leaks at 15% of the total. It's not a way to pass it. We still have to measure it. They just limit it to 15%. We can do the same test, call this the subfloor only test, and there is actually a separate test altogether, which is subfloor leakage, which you can use your fans for. Here we pressurize the room, and we neutralize the pressure across what we call the walk-down floor. We use a single fan to measure the leakage in the floor itself, and in some cases we can actually use this to find out what the below ceiling leakage area is. So 5 design tips. The PRV should be open early. Some PRVs really don't open until about 250, 500 pascals. They should all be tested to see when they open. I would say at least 30% of the PRVs out there don't open at the correct pressure. The sooner they open, the sooner that the pressure is relieved, so it's a good tip. Having the vent as high as possible is important. If we do that, we have to do a calculation to make sure that the suspended ceiling, if there is one, is vented properly so that the suspended ceiling doesn't get blown out when the system discharges. We should also be measuring vent area with our door fan in order to ensure that the vent area that we think we have is what we actually have. It's often much, much less than we think is there. And I guess to test the vents, test the entire venting path to make sure there's no obstructions, and to test electronic dampers to ensure that they will open. They should be tested annually to make sure they open, and then also the vent path should be tested, which you can do by testing the entire room with a lot of fan power, or you can create a box that goes over these vents and you can measure them that way. So you can measure them, if there's a bunch of them, you can measure them one at a time. When you do the evaluation, you will of course, find out if your vent is installed in the correct direction. And as I said, a lot of the vents in Europe have been installed backwards. They're not venting the largest peak pressure, which is negative. So that's something that needs to be taken care of. Here's the suspended ceiling, a little calculation here that shows you how to determine whether you have enough venting. So the pressure that blew the ceiling out could be created by a tight ceiling and a big hole above it, and it's using the ceiling as the vent path. The second thing is just the velocity of the agent coming out of the nozzles is sufficient to displace the ceiling tiles. And of course, running the enclosure calculations during the design process, using our venting calculator to do all the calculations in advance and try to figure out how you're going to get this enclosure to pass before it's even built, and resolve the issues when you have a chance to make changes. I think that's pretty well it. We give tech support to people that have gone through our training course. We have 3 levels, and we typically support to the levels that you're trained at. So by all means contact us, and we're more than happy to give you some information about that. So I'll just quickly take a look at some of the questions that people have asked. Let's see, someone asked about our mobile training unit. We do have some training courses in the Middle East. We have some in Southeast Asia. We've put hundreds of courses on in the U.S. Don't generally put them on that often here anymore, but we do have courses running in the Middle East. We have an agent there that puts them on a regular basis. And in Southeast Asia, we've had them in Singapore, Malaysia, Hong Kong, and so on. Contact us if you're interested in live courses, but our certification relies completely on the online training, which has a series of PowerPoints and videos and so on, which is all you need to learn this. It all uses the new software and all of our new equipment.